Okay, so welcome back again, and this is the Chipmaster, and in this video I will be working on a desktop, a Dell desktop computer system. Here it is. So I got it from another tech, and he said that it's not turning on. Right, he already tested the power supply and still didn't turn on, so he gave it to me to repair, to see if I can repair it. Alright, so it's an XPS system, right? XPS. So it's an XPS, as you can see there. It's an XPS unit, right? And then, so he said that it's not turning on. So I'm gonna take it apart. Right. Alright, so I'm removing these latches. Haven't long while I haven't taken apart a desktop computer system. Right. Okay, so I will start removing this part. It's kind of tight. Can this part be removed? I'm actually, oh, start from the power supply here. We have one more screw here. Whoops. Oh, I see. Oh, that one fell down. This should open like this. Oh, I see. Okay, there's a latch here. It's locked. I haven't pulled. I haven't. These Dells, they are so tricky. Just trying to open. This is also set to open, but it's not releasing. This part should be open along, so I did have to remove these screws. So once I release this latch to open, this to open, it should come out, but it's not coming out. I realized that I had to pull this piece forward and then lift to get it out, so I have to just put back these screws because they weren't necessary to. They didn't have to remove. So these power supply screws are not supposed to be removed. Alright, so it's all the way up. Now I'm looking at the board. As you can see, we have a dedicated graphics card here, and this is a most likely an NVIDIA. So I'll just remove the graphics card out the way. Alright, so as you can see, it's an NVIDIA graphics card. Alright, so I'll just remove these SATA connections, front audio, front panel connections. This is card reader, CPU fan, oh, case fan and the CPU fan. I'll make it stay. Don't have to remove that. This is the Wi-Fi. Don't have to remove the Wi-Fi. I will just remove the antenna. Right there. Alright. I'll remove the power supply since I'll be using my testing power supply. And this is USB, front USB ports. Alright, so I'll now remove the board. Yeah, pretty simple. Not that bad. Fan pulse, the CPU 12 volts, ATX 12 volt power supply connector there. Alright. Oh. Alright, so the board is now out. Sorry. So I have to get an angle. Okay, so alright, so the board is now out. So I will do some basic check on the resistances. Alright, so we have a PCH, we have the M.2, and we have another M.2 slot here, and Wi-Fi. We have PCI Express 16 and a PCI Express 1 speed, and this is a PCI Express 4 speed. Alright, so as you can see, we have a PCI Express here, 4, 1, 1 and 16. This is for the graphics card, and these are for like low speed LAN, USB and so forth. Alright, so we have the PCH here. So I need to see on the sticker here, it says it's a 8th generation. So this is most likely a socket 1151, because socket 1151 starting from Intel Series 6, which is the Skylake, all the way up to the Cannon Lake or the Comet Lake, Coffee Lake. Alright, so as you can see, it's an i5 8th generation CPU. Right, there you go. Alright, so it's an i5 8th gen CPU with a 2.8 gigahertz there of frequency speed. Alright, so I want to make sure that okay, so I move the fan out the way, so I'm gonna check some resistances now and see what we get on the resistances. Okay. Alright, so I'm at the multimeter now. Alright, just getting this. Right there. I think that it's okay. Alright, so here we go. So I have here, this is a PCH, right? And this is a 200 series PCH. And the board number, as you can see, is IPC, right, FL-VM revision A00. And this board was developed by Pegatron, and this is a Pegatron based motherboard in Taiwan, right? So this is a Pegatron based motherboard, as I said before, right? Pegatron. And it's developed by ASUS companies, along with ASUS, the Pegatron Electronics. Alright, so I'm gonna check here on the PCI Express slot, as we all know it, right? B, this is the B side, alright, and this is the A side, right? So B10, I get 86. That's a bit low. That's a bit low for the standby for the 3.3 volts VCC PIIM 3.3 volts for the PCH, right? This should be 1.0 volts standby, and I get 10. That's also a bit low. It normally should be about 34 or 33. Okay, so let's check VPP 2.5 voltage. That's okay. And this is RAM supply. No, that's 5 volt dual. This is RAM supply. Sorry, this is 5 volt dual. Right? If I remove the RAM, should be increased. See, I get 103 now. So that confirms that's the RAM power supply. Alright, and it should go back to the original value. We are getting 43. Okay, so CPU core Sorry, let's check the 12 volt side. It's ground. Right, so B12 ATX 12 volts is okay. Right, so ATX 12 volts is okay. Right, CPU core 000. Let's remove the CPU. Check again. 000. That's the ground. Sorry. This is the upper MOSFET. Right. So we are checking. So that's good. So let me put back the CPU back inside of the slot. And I get 0. So this resistance, this CPU has a very low resistance to ground. Right. This is the system agent. Okay, excellent. That's okay. VCC IO. Very good. So remove the CPU or unlock it. It should increase 21. VCC SA 6. Remove the CPU. Right, it's increased to 200 and 300 and 400. Okay, VCC IO increase. As you can see, this is confirmed that it's VCC IO pins. And I check it again. I get 21. VCC SA. Excellent. VCC GT for the graphics. I get 2, which is good. Right. CPU core and 12 volts, ATX plus 12 volts. I get 398. So the resistance is all good. But for this one, for VCC PRM 3.3 volts, I'm getting 87. That's a bit low. Alright, so let me connect the power supply. So I'm gonna do some hot checking now. Alright, so here we go. Alright, so I'm gonna give power. So I'm gonna turn on the board. This is the front panel pin here. Alright, so this is the front panel. So I'm gonna connect the fan, see if it spins. Alright, and the fan is not spinning, as you can see. Fan's not spinning. Alright, oh, I was in the way. Alright, I can make the fan stay here, doesn't need to be removed. Alright, putting back the fan. Alright, let's feeling if the PCH was getting hot or warm. Alright, so I'm gonna check some voltages now. Alright, B10. No voltage at B10. Right, so I'm getting 5 volts. Yes, I'm getting 5 volts there, as you can see. Just want to see if the meter. Seeing it better now? Let me adjust. Focus. Yeah. Okay, so B10. No voltage. Am I getting 1.0 volts VCC PRIM? Nope. I should be getting 3.3 volts here. Right? So as I said before, most of these Dell boards, they support the ERP specification. So the voltage will only come after pressing the switch. So I'll press the switch now. Let me remove the power and give power again. Right? I give power. First of all, let me check if the switch has 3.3 volts. Is 3.3 volt there? Yes. So we have 3.2 volts at the switch, right? So I'm going to short those to ground. Let me check if I'm getting 3.3 volts. Still not getting any voltage. So this is a no power, because I don't have standby 3.3 volts and I don't have standby VCC PRIM 1.3 volt, 1.0 volts. So that indicates to me that the board is out of order. So in order to get, for some boards, in order to get this 3.3 volts, after the PCH gets SLP, VCC RTC reset, right, SRTC reset, 32.768 kilohertz, then it will immediately and gets the deep sleep well, which is the VCC DSW underscore 3.3 volts, and deep or OK, then it will internally pull up the switch signal to the IO. So the IO controller is under the SSD here. And the IO controller here is having some discolored pins here. Looks like oxidation to me. Alright, so as you can see on the IO pins there, I thought I saw some oxidation, but it's pretty good. It's pretty fine. Alright, so as I said before, the PCH needs those working condition, right? Then after the deep sleep well is okay, then it will receive SLP source to turn on the light sleep power supply. So the light sleep power supply, which is 3.3 volts, VCC PRIM 3.3 and VCC PRIM 1.0 volts, right? So SLP source, so the power good which is going to enable the SLP source signal to turn on this VCC 3.3 volts, that power good will now going to enable the 1.0 volts for the PCH secondary standby supply. Then the board can be triggered. I wonder if everybody gets what I'm trying to say right here. Right, so this is the order, the working sequence of these boards that supports the ERP specification. Some boards doesn't need SLP source to turn on the VCC 3.3 volts, so that the Gigabytes and the MSI, right, and the ASRock motherboards don't use the specification. So the OEM boards or the ODM motherboards uses a specification, such as the Dells, the HPs, the Lenovos, right? Those are OEM, or we can call them ODM, because as you can see, Dell is printed here on the board. So Dell gave these schematics or the blueprint to Pegatron Electronics in Taiwan to create their OEM and ODM motherboard. This is our original design manufacturing. right? So that is what ODM stands for. And OEM boards are like the ASRoCs, right? The MSIs, right? The Gigabytes and so forth, and the and those brands. Oh yeah, pass. All right, sorry about that. So those, so that is the OEM and the ODM, right? So I don't think I can find a schematic for the. I'm not sure if a schematic is available for this board. I will check. Okay, so at the moment there's no schematic, so I will just have to use my experience. Right, so I'm going to check under the microscope for the RTC section. Well, before I can actually check it here, no. This is visual inspection. Alright, so this is the RTC battery, as you can see, and I get 2.8 volts, which is sufficient enough because after going through the germanium diode, there's normally a germanium diode for this RTC section. So after the battery gets, after the voltage leave the battery, it goes through a 1 kilo ohm resistor, then through a OR diode, which is we call it a germanium diode, right? Because the germanium diode have a voltage drop of about 0.001, right? A typical silicon diode has a voltage drop of 0.2 to 0.3 volt. So it will steal some of the voltages then in most cases, right? So the germanium diode is used for this purpose because this is a very important and precise circuit. If any fault is happening to this, if this fault appear to have a problem with the the diode here, which is the germanium diode, it will cause no trigger. So you don't want that. So they use a germanium diode instead of a silicon diode because the silicon diode will steal too much voltage from this RTC battery, and therefore it will not be able to save the parameters inside of the BIOS, right? And for the SRTC, which is a management engine firmware, which is inside of the PCH, right? The module inside of the PCH will not be powered properly, and that can cause all kinds of undescribable problems, or indescribable problems then in most cases, right? So you have, so this is why they use a germanium diode. So the germanium diode is a material that is made from germanium, which is from the a material such as like silicon and germanium. So germanium diodes have a lower voltage drop than a silicon diode. So please bear that in mind. Alright, so I'll have to go onto the microscope for this part so that I can explain it clearly. So I will check the signal without the power supply. So I remove the power supply. Right, so I'm going to head over now to the microscope. Alright, so let me switch over to the microscope shortly. Alright, so I'm now under the microscope. Alright, so this is the RTC battery here. Alright, so let me get back the multimeter back on screen. Alright, so we're going to check in sequence. So here, as you can see, this is the circuit that I'm talking about. So this is the battery, right? So the battery voltage is going to come through this 1K resistor here. Right, after leaving the 1K resistor, it will come through this path. This is an OR application of a diode here. Let me clean it, it's a bit dusty. Alright, there we go. So this is the path, right? So this is a 1K resistor going through this OR diode. This is a germanium diode. As you can see, this path here where you see this trace is coming to this input, and this input is coming from VCC PRIM. VCC, this is coming from the regulator, which is coming from the power supply, which takes the 5 volts, and that 5 volts breaks it down to 3.3 volts VSB. So this is 3 volts standby, right? And it's going to come through here, which is the output part of the diode here, right? And coming to this capacitor here to charge the RTC, VCC RTC. So I'm going to check here now. This is the path, right? So this resistor is a 1K resistor. I should get 2.8 volts here, as you can see, right? The other side is giving me 2.3, 2.6. As I said before, if this voltage drops below 2.4 volts, then it's not a valid it's not going to be a valid RTC supply because it's too low, as you can see. Right, 2.7 volts. Now it's coming to exit the germanium diode, and it gets 2.49. That's round that after 2.5 volts, right? And that's going to come here at this capacitor, and that's 2.5. So that is basically almost below the threshold, right? So this is a bit too low, as you can see, right? So I'm going to put another battery inside. That's giving me exactly 3 volts. Alright, so let me see if I can find a battery. Let me see the voltage on this battery. That's there, that's one is low. Let me find another one. I should have a new one. Alright, that one is dead. Alright, I seem to have to go and find a new one. Alright, so I'm now going to put a new battery inside of the slot. There we go, that's a brand new battery there. So let's check again. So I'm going to check the output side of the germanium diode. Alright, so our germanium diode is here. Alright. Alright, so this is a germanium diode here. And I'm now getting 2.8 volts. So after replacing the battery, the voltage increased, and now it's perfect. So that is the threshold. Remember, we get 3.3 volts here, right? After coming through the germanium diode, this is 3.3 volts here. Right, this is 3.3 volts here. After coming through the germanium diode, you see the voltage drop, right? 2.8. So that's 0.00, that's about 0.2 voltage drop of the voltage there. So that's normal. That's what we want, right? So that's going to be 2.8 volts, going to power the RTC well, right? And that's going to go to VCC RTC inside of the PCH. After the PCH get the VCC RTC signal, then it will turn on the crystal. So this is our 32.768 kilohertz crystal, right? So I'm going to check this crystal to see if I'm getting a voltage, right? And the voltage is correct, then the waveform is correct, okay? So I'm going to check at that 10 mega ohm resistor there on both sides. Remember, voltage on one side should be different from the other. So this is the, alright, so this is the, these are the picofarad capacitors. They are called resonant capacitors, which is used to offset the resonant frequency and to basically take that frequency without losing any integrity of the waveform of the frequency. So this part we're going to measure here. This is a 10 ohm resistor here. So I get 0.4 volts on one side, and the next side I get 0.46. Let's check the other side. Alright, I get 0.45. As you can see, there's also a 0.46 on the next side. 0.46. Right? As you can see, there's a slight delay. There is a slight delay when I'm checking this side. It goes to 0.36 first, then goes to 0.4, and this one goes to instant 0.4. As you see, that indicates that the waveform is okay and the crystal is okay. See, it goes to 0.37, then to 0.4, and this goes directly to 0.4, and that indicates that the crystal and the waveform is okay, and the RTC 32.768 kilohertz, as you can see on the board there, right? So it's right there, right? 32, right? 32.768 kilohertz. All right, next I'm going to check. I'm going to see if I can find the RTC reset and the SRTC reset signal now. Alright, so this is the PCH. So normally, it's normally located on this side. So I'll have to go and search each resistor with a capacitor in series. and see if I get the voltage. Remember, I'm doing this with the the RTC battery itself plugged in. Let's see if I get in a ground point here. Good, I get a ground point. Right, this is only the RTC battery plugged inside of the board, the only power, and this is called the DS5 state. Right, this is called the DS5, or you can call it the mechanical off state. Right, because at this time there's no power plugged into the board externally. Only the RTC battery is sending power to the board at the moment. Right, please bear that in mind. So this is called the DS5 state, or mechanical off. So I'm just gonna check. Here are some capacitors here. I have some capacitors here, so I'm going to measure around this area to see if I get back 2.8 volts. Aha, I found 2.8 volts, so that most likely is my RTC well. This one should be my, most likely my VCC, my DSW, sorry, this is the intruder. This is normally a 10 mega ohm resistor. Let me check here. On the next side, the voltage should be less. So once that is less, then that, you see, as you can see these traces, and it's going all the way back to the PCH. So this voltage should drop significantly. Take a look. Right, 2.6 volts. So it takes that 2.8 and dramatically drops it to, significantly drops it to 2.6 volts. So one side I get 2.8 and the next side I get 2.6 volts. So this is a 10 ohm resistor, a 10 mega ohm resistor most likely. So this is the intruder, right? Let me remove the RTC battery and go to the resistance gear on the multimeter, and this should tell me that it's a 10 mega ohm resistor. Let me see. Excellent. So it's 10 mega ohm resistor, as you can see, 10 mega ohm, and that is the intruder, right? This is a signal that is coming from way back from ICH4, from the socket 775 motherboards back in the early 2000s. This signal was generated, right? Intel now cancel this signal, right? But it's just used for reference only. Right, so I will now check these resistors and capacitors here in series, as I said before. So this side is a pull-up, this side is giving me 2.8, no voltage there. Oh, this is the pull-up side. So this is a 2.8 volts, right? And then this one, this is the pull-up, and then this is 2.8, and this one is a pull-up, and this one is also 0.2. That's not. That should be 2.7 volts because this is the RTC. So this is RTC reset. This is RTC reset most likely. Alright. And this should be, oops, camera up. Alright, so that's, sorry about that. Alright, so this is 0.2 volts. Let me check some other resistors in this area. Alright, no voltage there. Remember, I don't have a schematic, so this is going to be a bit more difficult because I'm not sure where they put the specific capacitors and specific resistors for me to check. Alright, no voltage there, but these voltage are not critical to me. So this is the area that is of interest right here in this section here. Right in this section here is of area of interest, right here. Okay, I'm just checking around these capacitors. Oh, that's where I checked a while ago. That's the RTC 32.768 kilohertz. This is not, should be SRTC reset. So I know I get VCC RTC. We check VCC RTC already. I get VCC RTC, right? VCC RTC is normally coming through a series of capacitors. Let me check this capacitor here. Right, no voltage there. Let me see here. No voltage here. No voltage there. No voltage here as well. No voltage there. I should get back the 2.8 volts at a capacitor. No voltage there. No voltage there. No voltage there. No voltage here and here. No voltage here. This is VCC RTC. So VCC RTC is coming through these two capacitors here, as you can see. This is VCC RTC, right? So this is SRTC reset, or RTC reset, I'm not sure. And this should be SRTC reset or RTT reset, I'm still not sure. This is the intruder, 2.8 volts, and it's taking some voltage to 2.59. This is the intruder. So this is my fault. This is definitely my fault area here. So I'm not getting back the 2.8 volts here. So this indicates to me, because as you can trace back this trace here, right, it's going all the way to the PCH, as you can see, under the PCH. So that means this section here is, my PCH could be bad. Could it be bad? My PCH is bad. Let's take a look at the die if there's any crack. Alright, it's not cracked. The die is intact. So this is my fault line. What I'm going to do, I'm going to jump a wire here and see if I get the 2.8 volts on the board. The board may work, hopefully. And if that works, then the repair is done. But I still feel that the PCH has a problem though. I don't think this PCH is fully working. The PCH is pulling down the voltage, so that means the PCH is broken, innit? Alright, so I'm gonna just run a jumper wire from the pull-up 2.8 volts to VCC to SRTC reset or RTC reset. I'm not sure because I don't have a schematic for this board. So I'm just going by experience here. Alright, just running a small jumper wire here. From one side of the resistor to the other side. And then I'll see what I get from here. Alright, so I don't know. Alright, so I'm just running a wire from one side to the other. Okay, guys. Alright, so I'm gonna give power from the power supply now. Alright, so I'm gonna plug in the power supply, ATX 24 pin, to give 3 volt standby, and hopefully I can get 3.3 volt VCC PRIM standby for the PCH. Alright, so I give power. Did I? Yes, I give power. Alright, so let me see if I'm getting 3.3 volts at the B10 pin of this thing, of the PCI Express slot. Yes, and I get 3.3 volts now. So as you can see, the RTC section was incomplete, so the PCH did not send SLP source. So the SLP source signal is actually coming from the PCH. Because it missed one of the working conditions of the RTC well, then it cannot move on to the next working condition, which is sending SLP source to turn on the 3.3 volts via VCC PRIM for the PCH. Let's check if I'm getting 1.05 VCC PRIM 1.0 volt now. Okay, so right, so the 1.05 volt. Exactly. Correct. So we're getting 1.0 volts. So VCC PRIM 1.0 volt is okay. So now I should be able to trigger the board. Right, so I should be able to trigger the board now, as you can see. Alright, so I'm going to trigger the board. Alright, so this is the front panel. So this is the switch signal. Alright, and I'm still not getting any fan spin. Alright, still no fan spin. Let me check if there's 3.3 volts at the switch. Yes, 3.3 volts is at the switch. But PCH is warm. Alright, this is CPU fan. The fan is connected. Alright, I'm gonna connect the 12 volts. Sorry, I didn't connect the 12 volts. ATX plus 12 volts. Alright, so there's a 12 volt there. I give power. There we go. Now the fan is spinning. As you can see, fan spins. There we go. Alright, the PCH is getting hot. It's now turning on. So let's check all supplies. Now it's working. All the supplies. Let me check all supplies now at the moment. Alright, so this is 2.5 volts, VPP 2.5. Excellent. Alright, this is the RAM core supply, 1.2 volts. Excellent. Alright, CPU VCC SA 1.0 volts. Perfect. That's good. VCC IO 0.95, I believe. Excellent. 0.95 is okay. Alright, this is core. Should get 0.8 volts here. And I'm not getting any CPU core voltage. Am I getting 12 volts? Yes, I'm getting 12 volts, but I'm not getting CPU core. Oh, CPU core 0.9 volts is there. Next side. 0.9 volts. Excellent. Next one. 0.9 volts. Now, so that indicates to me that the CPU power supply is okay. So now I'm going to let me check the RAM termination supply. Alright, so I'm going to give power. Let's check the RAM termination. VTT voltage. Alright, there we go. VTT voltage is okay or not? 0.6 volts. Sorry, that's 1.2. 0.6 volts. 1.2. 0.6 volts. There it is. So CPU. So the RAM VTT supply is okay. 0.6 volts. There we go. So 0.6 volts is okay, right? 2.5 volts is okay, right? The memory main supply is okay, right? VCC IO is okay. This is a up amp. This is called an up amp plus a MOSFET power supply mode. Alright, and we have VCC SA 1.0 volts, CPU core 0.9 volts, 1 volts. Alright, so I'm going to get the keyboard now to see if I'm getting display. Alright, so I'm plugging in the keyboard now. And I'm not getting any caps lock. Let me switch off and switch on again. Or it turns on by itself. Alright, so I'm waiting to see if I'm getting any caps lock. If the caps lock is there, the computer is fully working. Alright, so I'm not getting a caps lock, so I'm going to check the RAM. See something like a thermal pad that's inside of the memory slot. Alright, let's try another one. Alright, still not getting a caps lock. No caps lock is there. No caps lock, so I'll try another memory. Alright, so still not getting a caps lock. No caps lock. No caps lock. Let me just remove that out of the memory slot. But try in another slot. Okay. Oh, sorry. Alright, so it seems as if the CPU is not running code at the moment. So I will have to do further checks. I will have to do further checks to see what's causing the no display. Alright. So I'm not getting a caps lock, so the CPU is not, so I believe that the CPU is not running code. Alright, so it's no display. So it turns on, no display. So let me see if I'm getting clocks. So let me see if I'm getting a proper clock. This is 24 megahertz clock. Alright, so I get 0.4 on one side. And I get 0.4 on the other side. Check again. Yes, so the clock is working. I'm getting clocks. And the PCH is hot enough, very hot, to give display, as in functional heat. PCH is hot. Let me go over to the oscilloscope now to see. Alright, so I'm going to check if the CPU is now running code. Alright, so that's 1, 2, 3, 4. Alright, this is data. Alright, so I give power. Press the switch. I give power. Alright, so as you can see, the CPU, this is clock, sorry. So as you can see, I'm getting clock there, so the CPU is running code. Right, so the CPU is actually starting up. So the CPU is getting, all working condition of the CPU has passed. Right, so the only thing now is, and the proper communication is initialized between the CPU and the DMI bus instead of the PCH. Right, so I'm going to, for time, because if it is so long, I will have to pause and do some checking, and then I will tell you exactly what I did to get the problem solved. Alright. Alright, so I connected the graphics card and the original memory back into the unit, and I got the caps lock. That's all I did. So I was wondering if it was the BIOS or the DMI bus, or there's a communication between the DMI bus and the PCH was abnormal. So let me show you. So I connected the graphics card and the original memory, and then the fan increased its RPM, and once I heard that, I knew that everything was working. And there we go. So I have caps lock there. Look at that. Look at that. That's what I want to see. That's beautiful right there. That light is so beautiful. Look at that. Alright, so power it off. Alright, so that was a tricky one, not too bad. Alright, so I hope you enjoy that video, and I hope you that repair, sorry, and I hope you learn something, right? And as you can see, the PCH, I thought it was a PCH because I saw that the voltage from the SRTC reset or the RTC reset signal was pulling down the main battery voltage to the 0.2 volts. So I thought it was bad. So after running that wire, it worked. So I don't think I have to replace the PCH. So I think it's all good now because I get all working conditions, the computer displays and everything. So I hope you enjoyed it, as I said before, and in the next video I should be able to repair something for you. Okay then, bye.